the same thing, of course. And we cannot differentiate a function raised to a function using any formula because there isn't one. So we have to write natural log y equals 1 over x natural log tangent x. So we applied natural log to both sides, and we are going to differentiate y implicitly. So when we differentiate the left-hand side, we have 1 over y times dy over dx. And remember, the right-hand side is a product. We have to treat it as such. And remember, we already have a formula for this. And I'm hoping that moving forward, you will remember it. When we differentiate 1 over x, what do we get?
1 over x squared.
But negative. Negative 1 over x squared, not 2 to x to negative 3 or anything like that. Okay, so multiplied by natural log of tangent x. And plus 1 over x, natural log of tangent x prime will be 1 over tangent x. And I should write on the side secant squared. Okay, I'm going to write it here. And it's done. All I have to write is dy over dx, multiply both sides by y, and this is y. So this is tangent x raised to 1 over x, and in parentheses, all this thing. You just have to copy it. I'm going to condense it a little bit as natural log tangent x over x squared plus secant squared over x tangent x. And that's it. But again, just saying that's it is not enough. It's a complex situation in which we need to put time into it. Yes, Brandon?
Why is if we're differentiating 10x, when it should be secant squared x not over 10x? Yeah, there. Why is it over 10x?
So when I differentiate natural log of a function, I have 1 over the function times on the side the inner function prime, but it's over 1, so I condense it in a fraction. Better? Just because I'm overextending myself, as you know. But you can write it on the side if you want to. Okay, Ricky, you need more time? Okay. Perfect. Thank you. Okay, so for this one, again with the same thing, it's y equals cosine x raised to natural log x. We cannot directly differentiate, so we have natural log y equals natural log x multiplied by natural log of cosine x. You understand I skipped a step by bringing natural log in front already. So this is 1 over y. Is that okay?
Yes.
Dy over dx. And again, this is a product and has to be treated as such. The first one prime is 1 over x times natural log of cosine x, and plus the first one stays, and the second one is the same, what we just did. 1 over cosine x, but cosine x prime is negative sine s. I'm going to put it at the top, sine x. Final step, dy over dx. I multiply both sides by y. Cosine x raised to natural log x, and in brackets, I'm condensing a little bit. Natural log cosine x over x minus natural log x sine x over cosine x. And that's it. Any questions? Any questions? Once you go through several examples step by step and you understand them, you will have zero difficulties with this. You just have to find a little bit of time to do this. Any questions? So let's go back to the problem that we studied last time, and it's problem 2 on 233. 2 on 233, and we did not finish it. I'm looking at the previous notes. So 2 on 233, and we finished with part A, B, C, and D. And I'm looking at E. Find the total distance traveled during the first 8 seconds. So let me refresh your memory, and I'm going to copy here that we have t. So this is from part D. T and velocity, 0, 3, and now I'm going to put 8 this time, not infinity. We have 0, we have 3, negative direction. In other words, if you want to say it goes to the left in a negative direction and a positive direction, I will consider it going to the right.
So we're doing another table.
I only replaced it by 8 because in E, we're asked, the question in part E is asking us, find the total distance traveled during the first 8 seconds. So there is no point in going to infinity. So in E, total distance. Yes, any questions? Yes, Dakota, go ahead.
No, I was making a comment that the clock is still moving.
Oh, yeah, I'm not sure why. What happened to it? So the total distance is the absolute value plus another absolute value. So if the particle moves to the left or moves to the right, it doesn't matter to us. It's still accumulating distance.
There's a wasp in here.
Yay!
Right then.
So regardless of direction it's going, we have to accumulate distance. So that will be S of 3 minus S of 0 plus S of 8 minus S of 3. So between 0 and 3, so imagine the particle is here, 3 seconds goes this way, and then the next 5 seconds goes this way. So I have to determine the distance between 0 seconds and 3 seconds, and then the distance covered by the particle between 3 seconds and 8 seconds. So then, let me copy the formula. I don't have it anymore. So it was, I'm going to copy it up here. So S of t or F of t, doesn't matter. It was 0.01 t to the 4th minus. You have it. You don't have to copy it one more time. I just don't have it. So 0. I think, yes, just 1 0. T to the 3rd. Of course, I'm going to plug this in the calculator. I'm not going to do this by hand. I'm going to plug in the function in y equals, and that is 0.01 x to the 4th, and then minus 0.04 t to the 3rd, x to the 3rd power.
Where did that equation come from?
That's the function. We were given at the very,
Okay.
that was the first step we wrote. I just don't have the notes from last time. So we go to second and table. I always have to adjust this. What is happening here, please? That's not what I meant. I meant this. Okay. So second and table, and I only have 0. Of course, I'll get 0, 3, and 8. Did I write something else?
You did point. Oh.
Yes.
No.
Is that okay? Do I have an error somewhere? I did? It's 0.01. Good. So let's go back to the table. So I have 0, negative 0.27, and 20.48. So then S of 3, negative 0.27 minus 0, plus S of 8, 20.48 minus S of 3, minus plus 0.27. So the total distance covered by the particle is 0.27 and plus, and this is 20.75. Correct me if I'm wrong, please.
That's right.
So then the total distance will be 20. I think it's.
Is it going to be negative? 0.27?
21.
Okay. What was it?
21.
0.02. whatever measurement unit, and the measurement unit we have is feet. So this is the total distance covered by the particle. When we get to integration, you will see there is another way. I will refresh your memory on this. We'll go back to this problem, and I'll show you another way. But we are not there yet. We can't determine areas yet. Okay, this was part D. Draw a diagram. Okay, in part F, we already pictured the diagram. So at time t equals 0, the particle goes this way 3 seconds. And then goes back if this is 3 and 3 more and 2 more. T equals 8 seconds. That's the diagram. So this is s equals 0. And here is s equals 21.02. We can determine here, we already know this, at this point, it will be 0.27. So s will be 0.27 feet, and here will be s equals 21.2 feet, and here, of course, s will be 0 feet. That's the diagram. Okay, G, find the acceleration at time t, and then after 3 seconds, we want the acceleration, and we want the acceleration at 3 seconds. Can anyone give us the velocity? I don't have the velocity. I have to go back to the notes. What was the velocity? The velocity was, yes. So let's copy the velocity. I have to copy the velocity. 0.04 t cubed minus 0.12 t to second power. I had the function. I could have just determined it. I didn't have to do that. Okay, so can anyone tell us how to find the acceleration? Very good. So it's v prime of t or s double prime of t, the second derivative of the distance or the first derivative of the velocity. So we have 0.12 t squared minus 0.24 t. This is the acceleration function. Now we're asked to find a of 3. How do I find a of 3? 0.12 times 9 minus 0.24 times 3. I plug in 3. If you have this number, please give it to me. And please tell me the measurement unit for the acceleration. What is it? 0.36. Is it? Can anyone confirm? Okay, I'll do it.
That's right.
Is it? Okay, if anyone confirms that, that's fine. I trust you. Measurement unit, please. Remember, it's the rate of change of velocity, the velocity measurement unit, over time, with respect to time.
Second squared.
Excellent. That's the reason why it's feet per second squared. Excellent. Great job. Okay, then we're going to graph. We're asked to graph all 3. In a minute, we will. When is the particle speeding up and when it is slowing down? So let's discuss that. So H will be graph. And we will graph them all 3 on the same coordinate system with a calculator. But what I'm interested in is in the last question here, part I. When is the particle speeding up or slowing down? So let's discuss this. So here's the particle. It's going in a negative direction because the velocity is negative. And then it's going in the positive direction because the velocity is positive. But the question now is totally different. The question is, in this motion of the particle, 3 seconds this way and 5 seconds this way for a total of 8 seconds, when is it accelerating, when is it speeding up, and when is it speeding down. So if I go in this direction and I have a backwind, then I'm speeding up. It may not be the perfect example, right? When I come back and I have a headwind, then I'm slowing down, right? It's not my actual speed. So here's the idea. If two forces go in the same direction, the particle is speeding up. If two forces are against each other, then the particle is slowing down. Which two forces am I talking about? I'm talking about velocity and acceleration. If the velocity and the acceleration go in the same direction, even if they both go in the negative direction, it doesn't matter. The particle is speeding up in that direction. If the two forces are positive, this particle is speeding up. If one force is positive and the other one is negative, regardless of which one is positive or negative, the particle will slow down. So here's how we address this question. We look at the velocity and the acceleration. Since we're talking about 0 to 8 seconds, of course, we are going to look at 0 to 8 seconds. We know from some part D, I believe, that the velocity is negative between 0 and 3, going to the left if you want, and it's positive between 3 and 8, going to the right. Now I have to analyze and see what happens to the acceleration. The acceleration function, I'm going to copy it, and I will factor out 0.12 and t, 0.12 t, and then I have t minus 2. So look at the acceleration one more time, 0.12 t squared minus 0.24 t. So I factored out 0.12 t, and I have t minus 2 in parentheses. I'm asking you now, when is this 0? And you will definitely say it is 0 when t is 2 and when t is 0. Do you all agree? There is nothing else. When t is 0 or when t is 2, because we simplify by 0.12. Now, I would like you to tell me the sign of this expression of a of t between 0 and 2. So like plug in 1. Plug in 1 in here, just tell me the sign. That's all I care about. The sign between 0 and 2, bless you for the acceleration. Negative. Now plug in anything you want, even 10 or 1500, whatever you want, to the right-hand side of 2, and you will say positive. Now, I'm hoping you notice that we have to deal with 4 subintervals. One subinterval between 0 and 2, another one between 2 and 3, and the third one between 3 and 8. 3 subintervals, right? 0, 2, 2, 3, and 3. Good. What do I see on the first subinterval? I see that both the velocity and the acceleration are working together. They are both negative. They go into the same direction. What can I say about the particle? What is the particle doing between 0 and 2? Excellent. So between 0 and 2, right here, I'm going to say speeding up. Excellent. Now I see between 2 and 3. I see the velocity goes to the left, but the acceleration goes to the right. In other words, it's positive. What do you think happens between 2 and 3? Slowing down. What happens between 3 and 8? They work again together, this time on the positive side. So what happens between 3 and 8? Speeding up. Double E here, sorry. Speeding up. Excellent. So now, we can do that if you like. We can put all these 3 functions in the graphing calculator and graph them. However, I prefer, you can do that on your own unless you want me to do it. I prefer to show an example from the book. SIB, very similar. It's right here on page 226. Here it is on 226. So here is the distance function. Here is the velocity. And here's the acceleration. On this interval, 1 is positive, the velocity is negative, and the acceleration is positive. That's why the particle is slowing down. On this interval, between 1 and 2, what happens? Both of them are under the x-axis, so the particle, although it's going in the negative direction, we don't care, it's definitely speeding up. In the next subinterval, the velocity is negative, but the acceleration is positive. They are working against each other, so the particle is slowing down. And finally, between 4 and infinity, whatever that is, it's probably a certain number. Both of them are above the x-axis, obviously. They are working, they're helping each other, and they make the particle speed up because they have the same sign. Any questions about a problem like this? Any questions? Okay. So the next item that I would like, the next type of problem that I would like to show you is problem 32. And then we can move on. Yes? Pacific. So, very good question. If the acceleration is 0 and the velocity is positive, I'm cruising, right? It's like I'm just keeping it on cruise control. The speed is constant. It's not increasing, it's not decreasing. There's no acceleration. If the velocity is 0, then the particle is at rest, for sure. It's a very good question. Thank you. Okay, ready? So let's look at problem 32. Yes, Ricky? We are still in 3.7. Yes, yes, yes. We will not cover 3.8. It was covered in pre-calc. We will jump to 3.9 in a minute. But I would like to talk about one more problem. And I'm going to come back to this problem in 3.10 again. Okay, on page 236, let's read the problem. The cost function for production of a commodity is given to us. Find and interpret C prime of 100, and then compare C prime of 100 with the cost of producing the 101st item. Very important type of problem, and as I said, we're going to come back to it in 3.10. So I'm going to copy the function, which is C of x, 1200 plus 12x minus 0.1 x squared plus 0.30. As I see 3 zeros, correct me if I'm wrong. Okay, so this is a cost function of production for the production of something. Doesn't matter what it is, some item. When we determine C prime of x, we really determine a function that gives what? The rate of change of cost, excellent, with respect to the number of units we manufacture for any number of units. Okay, very good. The rate of change of the cost. It's in dollars per unit. In dollars per unit. Or the instantaneous rate of change for every x. This is also called the marginal cost. Yes, it has another name, which is the marginal cost. In part A, we're asked to find and interpret C prime of 100. So we are asked to find the marginal cost first. We have to find C prime of x, which is 12 minus 0.2x minus plus, 0.1215x squared. So we found the marginal cost function, and now they're asking us to find C prime of 100. We will find C prime of 100, but we also want to interpret it. So we'll write the interpretation in a minute. So this will be 100 minus 20, and plus, this will be 4 zeros plus 15. So I got 115 minus 20, and I got 95. Please correct me if I'm wrong. Dollars per unit. Correct me if I'm wrong, please. Anytime, not just now.
You did number 31 instead of 32.
32.
She's right. I copied the function from 31.
It's okay.
So yeah, it's Pi Day. I'm allowed to. No, I always do that. So please keep an eye on me. It's too late. Sorry. Sorry. This is easier to do than start from scratch. I'm sorry. Thank you, Ariana. I apologize. Okay, yes, she's right. I copied the function from 31. My apologies. Okay, so stick with me. So in this case, we're asked to find C prime of 200. Okay, that I can do. So we are asked to find C prime of 200. So 12 minus this multiplied by 2. What did I do? Why did I copy here 100? Sorry. Okay, it's right. It's the right time then to go back and do it again. So C prime of. Why did I write 100 and no one said anything? It's not your fault. What am I doing? So the function is correct. The function is fine. I just plugged in something else. Where I was looking, I don't know. Okay, 200. So 12 minus 0.2 times 200 plus 0.0015 times 200 squared. Okay. Obviously, I can't calculate today. I'll wait for you to give me the answer. So in part A, we determined the marginal cost. In part B, we're asked to find C prime of 200. Okay, so this is part B. C prime of 200. And I trust you, whatever you give me, I'll put it in. But please make it exact and accurate. Can anyone give me this number? My apologies.
32.
Okay, $32 per unit. Thank you very much. What does it mean? What does it mean? This predicts the cost of the next item. If we manufacture 200 units, what will be the next item then? Exactly. 201st item. Part C. Compare this number with the cost of manufacturing the 201st yard of fabric. In that case, it was yard of fabrics. Okay. Ready? So this is a prediction. In other words, an approximation. This is what it means, a prediction, approximation. It's not an exact. If I want to determine the exact cost of the 201st item, how will I do it? I will calculate the cost for 101, from which I subtract the cost for manufacturing how many? Exactly. So the cost, the exact cost, not the prediction, not using the derivative, but the exact cost of the 201st item is, I will calculate the cost of producing all of them 101, and calculate the cost of producing all of 100, subtract, and that will be the exact cost of manufacturing the 201st item. Is that clear? Yes? Okay, so let's determine C of 101, which we do not have. And let's determine C of 100, which we don't have. And since you know I like this better, I will clear and I will put the cost function. 1200. Yes?
It says supposed to be 201 and 200.
And then 200 instead of the 101.
Yeah.
Yes, of course. I told you, I'm looking at a different. I am looking at a different. Today I'm allowed. Next time I won't be. Sorry, my apologies. Of course, 200. So back. My brain was thinking of still the same thing. Of the 100. Okay, minus 0.1. I'm glad you are on track. And keep me on track too, please. And x to the third. Okay, so finally I want 200. And I want 201. And I will immediately subtract the 2. So, yes, please, Savannah. I'm sorry, Vanessa.
Okay, I have a question with
Yes.
the formula you plugged
In here,
yeah. Is that 1200?
it better be. Yes.
No, but I'm sorry, like, where did you get the 1200 from? Which one?
That's the formula, the function. That's the function.
Oh, okay, the original one. Okay.
Is that okay?
Yeah, I was just making sure.
And now I don't trust myself with anything. I'd rather go back and check everything now. So as you see, we are subtracting. Am I okay now?
Yeah.
For now, right. So 3632.2005 minus 3600. Am I correct?
Yeah.
Okay.
Yeah.
At least for now. So we have $32.2005 per unit. What would you say? Are you happy with the approximation determined with a derivative? I am. Look at 32 versus 32.2005. I am happy, right? Now, if you say, if it's a life and death situation, and this 0.2 can kill 1,000 people or even 1, I'll say I'm not happy with this error. This is exact and that has an error, minus 0.20, right? But when it comes to yards of fabric and like in this problem, I'm happy. I'm happy with this because I can determine it easier than determining this. Any questions? Any questions?
Can I see the formula you put in there?
Yes? In the,
In the Y you put in
yeah, it's the cost function, which was given to us as 1200, unless I copied something else, plus 12x minus 0.1x squared plus 0.005. 3 zeros, 0.0005x cubed. Is this okay? Okay, our next section is not 3.8, but it's 3.9. Related rates. We're going to spend some time on related rates. So I'm assuming today and possibly one more session, or at least another half of session. It's a very wide topic. What does it deal with? When we talk about related rates, we talk about changes of different variables that happen at the same time. And they can trigger one another. For example, imagine that I have a balloon and I pump air in the balloon. What changes? Pressure. Pressure, volume, radius, surface area, right? Circumference, if you want, but the surface area for a sphere. A lot of changes. Okay. Here another example. Let's say we're traveling north and somebody else is traveling, let's say, east. So somebody travels north, somebody travels east. The distance between these two people changes with respect to time. 3 things change here. The distance, it's the rate of change with respect to time. This distance is the rate of change with respect to time. And the distance between the 2 people changes. So all these are triggered. Okay, they are related. Related rates. So let's start with this, to illustrate this with a simple example, like what I just said. So let's choose a problem. We are on page 248. Here is a problem with 2 cars start moving from the same point. That's one situation. A man starts walking north, a spotlight on the ground. Which one would you like to start with? 16? Very good. So let's start with 16. So this is problem 16 on 248. So let's read the problem. A spotlight on the ground shines on a wall 12 meters away. So here's what I know. That's what I know so far. There is a spotlight right here. There is a wall 12 meters away. Next sentence. If a man 2 meters tall, okay, so there is a man 2 meters tall, walks from the spotlight toward the building at a speed of, I cannot draw a man, sorry. So he walks this way at a rate that is given to us 1.6 meters per second. How fast is the length of his shadow? As you see, at any point in time, if he is here, for example, right? So if he is in this position, this is the shadow on the wall. If he is in this position, this is the shadow on the wall. So obviously, the closer I get to the wall, the smaller my shadow is. The further away I am from the spotlight, the smaller the shadow is on the wall. Would you agree with that? Perfect. So then, we're asked, how fast is the length of his shadow on the building decreasing? Obviously, we know it's decreasing, so the rate will be positive or negative. Decreasing, right? It will be decreasing, negative. On the building, decreasing when he is 4 meters from the building. So the rate of change, this is the question, of shadow when distance is 4 meters. This is just taking notes. I did not start the problem. I did not read it again. I did not identify anything yet. This is just the idea. Now I'm going to read it again. Ready? A spotlight on the ground shines 12 meters away onto a wall. If a man 2 meters, see? If a man 2 meters tall walks from the spotlight toward the building at a speed of 1.6 meters per second, how fast is this? Let's give it a name. I'm going to give it, I don't know, H. How fast is the length of his shadow on the building decreasing when he is 4 meters from the building? Any questions so far? Yes?
Would it be positive because him and his shadow are getting closer to the building?
We are talking about the rate of change of this. Anything that is diminishing in volume or capacity or whatever, it must be negative. So if the shadow would be increasing, then the rate of change will be positive. If the shadow is decreasing, the rate of change must be negative. Is that better? Is that clear? Okay. Perfect. So here's the idea. All I have at this point is this, which is 2 meters. I have this, which is the height. I have this, which is 12 meters. And I have this piece that I'm going to denote by X. Before we even address what happens here and how we proceed, here is our first thought. if I'm asked to find the rate of change of this with respect to time, it means that I have to create a relationship, an equation that has this in it, as well as everything else that I'm given, whatever that is. So one more time, I'm asked to find the rate of change of this. Obviously, it's a function. It's a function of time. So here's the spotlight. I'm going towards the wall, and this changes. If it changes every second, every instance, it's a function. And it's a function of time. Otherwise, it would be fixed. So this is not a function of time. This doesn't change. It's fixed. But the shadow, my shadow on the wall changes with respect to time. So that is a function with respect to time. That is a function of time. So this is a function of time. What else changes in here? This. I'm walking away at a speed of 1.6 meters per second. So this x changes. It's a function of time. It was initially 0, and then it's a meter, and then it's another meter, and it's another meter at every instant. So this is a function. So this is a function with respect to time. I'm walking. I'm changing my distance away from the spotlight. This changes at the same time. These must be related. Because when I walk, that changes at the same time. These two change at the same time. I'm not saying at the same rate. Yes, Brady?
What is x?
The distance that I cover, I'm right here. I'm right on top of the spotlight, and I'm walking towards the wall. This changes. It's a function of time.
So isn't that the same as the 12, the distance from you and the wall?
No. This is the domain of that function, from 0 to 12, because then I hit the wall. So it's only from 0 to 12. But the function, that's the domain of the function, for x being between 0 and 12. But this changes with respect to time.
So that's at any particular distance before you touch the wall?
Exactly.
Okay.
At any instant.
Okay.
Correct. This would be the distance. It's a function with respect to time. So I know now that x is a function of time, f, let's say. I know h is another function of time, g of t. And I have to determine a relationship between them. Notice that this distance does not come into play. Everything that comes after the word when in any of these problems has to be disregarded till the very end of the problem. How come? Because if I don't have the function and I don't have the derivative, I cannot plug in 4 meters in anything. I don't have the relationship yet. So can anyone tell us in short, if this is a right triangle, which it is, and this one, which is a right triangle, which it is there a relationship between these two triangles? Is there something we remember from geometry? The small triangle, which is right, and the big triangle, which is also a right triangle. Correct. We are talking about similar triangles. The small triangle, it's similar, not equal, not congruent, of course, with the big triangle. Why? Because I can show that they have 3 congruent angles. These 2 angles are the same. This angle is common, which means the same. And this angle is common. I shouldn't say common, equal. Therefore, the small triangle and the big triangle are similar. If they are similar, then we can write proportions with their sides. But please be very careful how you do that. Let's do this together. Let's start with the small angle, the common angle. What is the opposite side of the common angle in the small triangle? 2. What is the opposite of the same angle, but this time in the big triangle? H. Moving on to the next pair. But there is nothing I can do with these 2. Why? Because I don't have this, and I don't have this. So the next one is not important. Let's move on to the third one. Remember, the tops have to come from the same angle, so from the same triangle. So I am looking at the small one. What is the opposite of this blue angle in the small triangle? X. And now I have to go to the same angle, but this time in the big one. 12. So careful, one more time, in order to show the proportions for similar triangles. You have to have the top, all sides coming from one triangle, which we did, to an X, and this one wasn't necessary. And the bottom ones from the big one, or reversed, but you have to be consistent. As you see, H, 12, and this. You cannot write 2 over H equals 12 over X. That would be wrong. So one more time. Small one, opposite 2. Small one, opposite H. Blue one in the small one, opposite X. Blue one in the big one, 12. This is the relationship we need. And of course, we will do what? Because this is a proportion. Cross multiply. 24 equals X times H. Okay. Now, of course, we will differentiate both sides. Remember, the right-hand side is a function of time. X is a function of time, and H is a function of time. A product of 2 functions of time, I meant to say. So the left-hand side is 0, but the right-hand side, yes, the first function prime, dx over dt times H plus X times dH over dt. Now you see how important it is to use this notation. I know it would have been much easier, X prime, H prime, but it's not a good idea. So now, coming back to our question, we're asked to find the rate of change of the shadow, blah, blah, blah. So what am I going to solve this for? This is what I want. I'm asked to find dH over dt when X is, and we'll establish what it is in a minute. First, I will move this term to the other side, negative H dx over dt equals X dH over dt, and finally solve for dH over dt, which is negative H over X times dx over dt. I'm happy because I found a relationship. I found the derivative of H with respect to time. All I have to do now is plug in some numbers. But now I have to be careful. So we are told that the man is 4 meters away from the wall. What is X? What does X equal to when the man is 4 meters away from the wall? 8. Very good. So when X is 8 meters, this will be 8 meters. In a moment, we'll get to H. Can anyone give us this? Very good. That is what this is. The man, this X, yes, Vanessa, go ahead.
So 8 meters, is that a given in the top?
No, 4 was given. The man is 4 meters away from the wall, but I'm interested, I cannot use this. I've never even used this distance. My distance is this. It's what the man is covering.
Yeah, that makes sense. Okay.
I can use this. I only knew this. Very good question, actually. So this is what we are given initially. So if this is the distance from the spotlight, because the man walks in this direction towards the wall, obviously 1.6 is the rate of change of distance with respect to time. It's dx over dt. Excellent. So this is indeed 1.6 meters per second. I am missing one piece of information and we're done. I'm missing this. No, not really, because now I can determine that particular instant in which this is 2. This is now 8. This is 12. And this is h. In other words, I don't have to go that far. I have the relationship. 24 equals x times h. When x is 8, how much is h? 3, right? 3 meters. So I have that too. And I can go back and replace this by 3. Don't trust me with numbers today, so please multiply 3 by 1.6 and divide by 8 and give me the answer. I'm kidding. I can do this one, I think, today. Negative point. Negative 0.6. Measurement unit. Remember, it's a distance with respect to time. The rate of change of distance, this height with respect to time. Meters per second. As expected, because it's a decrease, it decreases, it has to be a negative rate. Any questions?